A formal system architecture that includes irreversible failure modes is modeled by augmenting the state space with an absorbing cemetery state. The stochastic process is defined on the probability space and takes values in the union of the live state space and the absorbing state. The system is alive at time t if and only if the trajectory has not yet entered the absorbing state. Conditioning on survival means restricting attention to the sub-ensemble of trajectories that remain in the live state space through time t. The conditional expectation given survival is not equal to the unconditional expectation because the two averages are computed over different subsets of the probability space. The absorbing state formalizes irreversible failure in a system model. It is a state from which no transition to any live operating state is possible. Once entered, the trajectory remains there permanently. The stopping time is the first entry time into the absorbing state. Before the stopping time, the trajectory is subject to the full transition law of the live dynamics. After the stopping time, the trajectory is constant at the absorbing value. The live dynamics and the post-absorption behavior are structurally distinct and must not be conflated. The survival event is the event that the system trajectory remains within the live operating region through the required operational horizon. This event is measurable with respect to the filtration generated by the process. It is determined by the history of the trajectory up to the relevant time. The survival probability is the probability measure of this event. Conditioning on the survival event defines a new probability measure on the subset of trajectories that survive. This conditioned measure alters the distribution of every subsequent state variable. The system's statistical properties are different on the survived sub-ensemble than on the full ensemble. Conditioning on survival produces a new probability measure that differs structurally from the original process law. Under the conditioned measure, the distribution of the state variable at any future time is the conditional distribution, given that the stopping time has not yet occurred. This is not merely a rescaling of the original distribution. The conditional distribution selects trajectories that satisfy a specific path-level event and places different weights on future states. The conditional transition rates, conditional mean, and conditional variance all differ from their unconditional counterparts. A design calibrated to unconditional statistics will be miscalibrated when deployed in a context where survival is a requirement. Conditioning and marginalization do not commute in the presence of absorbing states. Marginalizing over the survival event before computing state statistics yields the unconditional distribution, which includes the probability mass assigned to failed trajectories. Computing state statistics conditional on survival and then using those statistics for design yields a result restricted to the live sub-ensemble. These two operations yield different results. The order in which conditioning and averaging are applied determines the answer. System architects must specify explicitly whether their performance criteria are defined over the full ensemble or over the conditioned survival sub-ensemble. Survivor bias is the systematic distortion that arises when system performance is evaluated only over the sub-ensemble of trajectories that have not yet failed. The observed performance of surviving systems exceeds the true unconditional performance because failed trajectories have been removed from the sample. This distortion is not a measurement error. It is a structural consequence of conditioning on survival. It implies that performance data collected from currently operating systems cannot be used directly to estimate the performance of the full population of systems, including those that have already failed. Accounting for survivor bias requires an explicit model of the failure mechanism and the stopping time distribution.